my dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Center, and YouTube channel, Kumar. So, I'd like to welcome you all to our international physics webinar. Good evening to all. So, hope you are well and safe from Corona pandemic. So, as you know that we are staying in a Corona pandemic situation and situation becoming worse day by day. So, we have to maintain our health rule. So it's very difficult for us to continue our academic program inside the campus. So we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology has started its online program, including international physics webinar. And we have successfully completed our 240th international, so 50th international physics webinar. Today it's our 216th international physics webinar. And today we would like to welcome you all through a joint session between our Department of Physics, Pabna University of Science and Technology, and the Variable Energy Cyclotron Center, India. And we have with us here today Dr. Gopal Mukherjee, sir, Scientific Officer, Senior, Physics Group, Variable Energy Cyclotron Center, India. And he has already connected with us. So I'd like to welcome our speaker. Sir, good evening, and thanks for accepting our invitation. And it's my pleasure and honor to host you in our international physics webinar. So before going to you, I would like to introduce you with our student and the viewers. So dear student and viewers, I think you have already come to know that the title of this today's international physics webinar, that is the gamma ray spectroscopy to probe the fascinating world of nuclear structure. And our speaker is Dr. Gopal Mukherjee, Scientific Officer Senior, Physics Group, Variable Energy Cyclotron Center, India. And he has completed his PhD from Vishwabharati University, India. And then he joined as a research associate at TIFR, and he stayed there up to 2000. And then he got another postdoc at UML, USA, and he stayed there up to 2001, and then he got another postdoctoral fellow at ANL, USA, and then research associate as the SINP, and then postdoctoral fellow in France. So now he is currently working as a senior scientific officer at BCC. And you can see his research interests: gamma ray spectroscopy and nuclear structure, nuclear reaction and dynamics, nuclear structure data. He has a lot of publication. So I think you will enjoy our this session and learn a lot of things about the gamma ray spectroscopy. So thanks, sir. I'd like to welcome you again, and it's your time, so you can start your session, sir.
Okay. So can you see my slide?
Yes.
First of all, the technicality. Yes. So is that full screen?
Yeah, full screen.
Okay. Okay. Thank you very much, Dr. Pretam Kumar Das, and I thank Pretam Kumar Das for inviting me for this in this venture of giving me some.
It's my pleasure, sir.
Or discussing something about gamma ray spectroscopy and nuclear structure. Am I audible?
Yes.
Okay.
Yes. Everything okay.
Thanks. So and yeah, so and this is actually, I think, very good beginning. I mean, he has done a very good work in organizing these webinars, and I have seen some of these webinars over internet. And I saw these are very nicely organized webinar. I don't know how much I can do justice to that series. But in this corona pandemic, I think there is very good. I mean, this Dr. Das must be thanked by everybody that he is giving this opportunity to the students to hear many scientists all over the world, and including the Nobel laureates. So, and I'll try to today speak something about the nuclear structure and gamma ray spectroscopy. And if you have a question at the end, you can ask. You are welcome. And of course,
Yes,
here
we
is
can
my
discuss the question
email
later.
address.
Yeah.
Okay, yeah. So at the end, and here is my email address. So If you have some questions later on, also you can email me for anything. And I understand that this seminar is mainly for the students, graduate students, and I kept my slides and I prepared my talk accordingly. So the people who are little bit in the experienced person, so for them I apologize to them from the beginning. So let's begin our journey to the fascinating world of nuclear structure and how do you prove it from gamma ray spectroscopy. Okay, now let us start by asking a question of what all objects are made up of. And this is a question that you and me are not asking. This has been asked for many years, thousands of years ago also. And accordingly, we have some from even for prehistoric era also. And early Indian philosophers classified matter in the form of five basic elements. So the question is, what are the basic elements from which all the objects, all human beings or non-human beings are made up of? And so there was something called Pancha Tattva, and which are the air, earth, fire, sky, and water. And these questions have been asked several times over and over again. But in the history, the concept of atom has got two schools of thought. One is from the Greek school of thought, and another from the Indian school of thought. So when I say India here, so it's not Bangladesh, not India, it's not Pakistan, it's all undivided Indian subcontinent, right? And in the Greek in the Greek part, there's a Leucippus and his student Democritus, so who coined a word atomos, which says uncuttable, and they gave some hypothesis and about this matter, which what is composed of this uncuttable atoms and things like that. And in the if you go through Google and search for something, so you will get Acharya Kanad, and who lived somewhere between 6th and 2nd century. So this is not known very this is not very well known, but it is known there is a school of Vaisheshika school and of Indian philosophy, and there are Vaisheshika Sutra, and he gave a very nice concepts of atom, that everything can be subdivided, but there exist small entities, and we call it Parmanu, that cannot be divided. Actually, here I did not get whether this word Parmanu was coined by Acharya Kanada or not. But the things, the concepts that he propagated was very meticulous and is true. Today itself. So, but if I now move ahead from there, so but the again the same questions: what all objects are made up of, and what is the smallest entity that is undivided, that cannot be divided. So in that quest, we moved from the atom to nucleus to the nucleons to quarks, and I don't know what is hold in the future. And so we are discussing here this atomic nucleus. So this atom, and there is inside there is a nucleus. So this picture of atom and the nucleus was this modern atomic structure is by Ernst Rutherford and Niels Bohr, and in which there is one a nucleus inside an atom, and the electrons are moving around it, and there is a very vast amount of space which is in between the electrons and the nucleus. And in this subject of atoms and nucleus is actually so interesting that it has got several Nobel Prize in the history of that, and it begins from the beginning of the history of Nobel Prize, basically. And Niels Bohr received Nobel Prize in 1922 when he has for his services in the investigations of the structure of atoms and of the radiation emanating from them. So that is the picture that he got, and that picture remains this way since then. So what is an atomic nucleus that we are discussing today? So the nucleus is a many body quantum system. So there are two kinds of systems, right? This is one is quantum systems, and a which is microscopic system, and the macroscopic world, which is the classical world. And this nucleus is actually in the quantum world, and it is made up of protons and neutrons. So inside that there are protons and neutrons which are held or bound by strong interactions. So there are four interactions, right? So gravitation, strong, weak, and electromagnetic. So there these proton and the interactions going on between the protons and neutrons, which is holding them together, is by strong interactions. And they are stable and radioactive nuclei. So these, in fact, you can see that these all the four interactions that you can get manifested inside the nucleus. So we can get all flavor of all the four interactions in the if you study the nucleus. And this nucleus is actually a very good laboratory to test the symmetries of quantum world. So there is in quantum mechanics we talk about different symmetries, the rotational symmetries, the symmetry of various time reversal symmetry, and all those things. So, but the practical applications and manifestations of those symmetries that you can get in this nuclear in the world of nuclears, and they manifested in a very beautiful ways, and I'll give some examples probably. And so inside the nucleus, the protons and neutrons move in the orbits, in different orbits. Now, what are the orbits and things like that? So I come to in the next slides. So again, so this is for the undergraduate students. So this is quantum states of nucleons and nuclei. So as I said, there are two objects. We can classify into two groups: this classical objects and the quantum objects. There are several certain differences between them. But what the striking difference, which I actually fascinates me from the beginning, is this: that their energies are actually quite differently manifested. In classical object is like a ball, a classical ball when falling through this inclined plane, it comes down with continuous decreasing energy and comes to rest. But if you have a quantum object, so it if it is at a high excitation and comes down here, so it does not come in a like these quantum objects, but it comes through as if in stairs. So these stairs, if these stairs actually, so let's go the classical, because we are talking about the nucleus and nucleons. So these are the quantum objects. So in these stairs, if I put these stairs in the as a levels, so these are the orbits. So since the protons and neutrons are the quantum mechanical objects, so they have this, or they are in these orbits, or the stairs, or in this on the stairs of different energies. And since you have several protons and neutrons inside the nucleus, so they are arranged in these orbits like this. So inside the nucleus, there are orbits, and their protons and neutrons are in this way. And if this arrangement, the initial arrangement of the nucleus is, we call this energy of the nucleus as the zero energy or the ground state energy. So the nucleus is also a quantum mechanical system. So then also it has a level or the orbit, not orbit, but it is a state, nucleus state, which is the ground state. Now what happens? Okay, but before that, so it has a also, what is this? This and the this state is called the. It has certain quantum numbers, which is angular momentum I and parity pi, which can be plus or minus. And this angular momentum is what? It is this last nucleon, this either proton or neutron, which is in this orbital. So the corresponding to this orbital, it has the energy E8 and J8 pi. So this J8 pi of the will be the angular momentum for this state, for the nuclear state. Now, what happens if we give energy to this nuclear system? Then it excites this nucleon. So this energy is transferred to this nucleons, maybe transferred to this nucleon, and this neutron can be excited, this nucleon can be excited to another state. So now this is a different arrangement, and it has a different energy because one has gone to a different energy, this from E8 to E9, which is higher energy. So that is a excited state of the nucleus itself, because the arrangement is also different. And so it has another state which is an excited state, which has a different energy, this delta E energy, which was given here. And because now this angular momentum of that state is defined by this odd particle here, so now this state also have a different angular momentum, and this angular momentum is by J9, because now this is in the ninth orbital in this example. So that way it you can generate the excited states of the nucleus. So these are the excited states of the nucleus, and these are the excited, these nucleonic orbitals. These where these nucleons are in this orbital inside the nucleus. Now, this is actually all these things actually put in mathematical form, in the mathematical form, and in a model, and could be the magic numbers could be explained very well. I'm not going into into the mathematics, but this is true, this is done very long ago, and but this is true even for now, and this works very well for the nucleus. And for that, this Nobel Prize was given to Eugene Paul Wigner, Maria Gephardt Mayer, and J. Hans D. Janssens for the nuclear cell structure, for discovering discoveries concerning nuclear cell structure. So this nuclear cell structure actually a very good and very pioneering discovery from which you can understand the nucleus. Now, how this is manifested in the nucleus itself, or can we understand from the experimental thing, because this is all theory, and that is how I told you. So consider this is a real nucleus, 209 Bismuth, in which there are 83 protons and 126 neutrons. So 83 means there is an odd proton, right, outside this even number 82 and 126. So as my other example, and consider the other example in which have the odd particle. So this odd particle actually in those orbitals in the previous slide, which I showed the orbitals, which Maria Mayer and Hansen they gave from this theory. So that will lie in this H9 hub orbital, a orbital which is called H9 hub. So as I told, this the angular momentum of the nucleus will be the angular momentum of the state in which this new odd neutron or nucleon is. So that corresponds to the H9 hub orbital, and this H9 hub actually we know that corresponds to 9 hub minus. And experimentally also it is found that you see for this 209 Bismuth, the ground state or the zero energy state is 9 hub minus. So that is very nice. But that is not all. We have to understand all the other things. And all these levels are actually nuclear, or levels belongs to 209 Bismuth, which is which is experimentally found. So these are real states. And now if you give energy, then as for my previous example, it can, this odd nucleon can go to the 7 up state, and so I should get a 7 up minus state, the first excited state, and that is what it is experimentally found, the 7 up minus. And similarly you can go on to I13 half, or let's say 5 half, and accordingly you get I13 half corresponds to 13 half plus. So that's it. If 5 half corresponds to 5 half minus, and this is the 5 half minus state. So that's how you get all the states and can relate with the cell model all the states in a real nucleus with the experimentally observed states. And you see there is a gap between your 13 half and 5 half here, and that is also reflected here in the real nuclear case. There is a gap between 13 half plus and a 5 half minus, large gap. There is no state in between. This very good, nice correlation between what theory gives and what we see in the experiments. And this is such type of nuclear excitations are called the single particle excitations. But this is for this from the spherical nucleus, spherical cell model of the nucleus. So, and that is true for the spherical nuclei. But nuclei can have different other shapes, the non-spherical shapes. So it can have deformed shapes, like a quadruple shape, or like a PR shape, octuple shape, or all in these two shapes are symmetry. There's a symmetry axis in this shape, so these are called the symmetric shapes. But there are some triaxial shape in which there is no symmetry axis. So these different shapes, and people have imagined that this kind of shapes can nucleus can have. Now it is our aim to find out in experiments whether you can see this shape or whether you can see these different shapes. So this deformed nucleus can rotate. I'm sure when in a childhood you have rotated this kind of top, right? So like that, a nucleus can also rotate. And then if a whole nucleus can rotate, then this motion of the nucleus as a whole, so this all with all protons and neutrons together, it is rotating. So that is why it is called the collective excitations of the nucleus. So when the nucleus rotates, so the deformed nucleus can have a collective excitations or can have collective mode. And you see there are not only this rotation, there are different various other collective excitations or collective modes in the nucleus. This can have. This is the artistic view. But you see there are these are beautiful motions, and it is like there are some disciplines in these motions. And in these motions is like the dancing of the nucleus. And as I'm talking in Bangladesh, right? I mean this Pabna University, and so you must have uh, seen this, read this somewhere. নৃত্যেরও বসে সুন্দর হলো বিদ্রোহী পরমাণু, পদযুগ ঘিরে জ্যোতি মঞ্জিরে বাজিল চন্দ্রভানু. So it's like dancing. So Rabindranath Tagore says the rebel atom becomes beautiful when it's dancing. So this dancing nucleus is like very beautiful. And now our aim is to observe this beautiful dance of this nucleus. But can you see them? But you cannot see them in your eyes because there's not enough powerful microscope to see them in your eyes. So what you can do, you have to find out the observables and tools to quote and unquote see this. And how do you do that? And that is the second line. This পদযুগ ঘিরে জ্যোতি মঞ্জিরে বাজিল চন্দ্রভানু. So what he says is that this Chandra and Bhanu means this moon and the sun. So they give lights, this jyoti. Why? Because they are in their feet. They have this monjis, this nupur, this anklet. So they have this light radiating anklets, and that's why this Chandra Bhanu gives the light. So this nucleus also has this radiating anklets, and so what they radiate? So they radiate gamma radiation. So now if we can see these gamma radiations which is emanating from this nucleus, then we can see this beautiful dance of the nuclei. So let's see how we can do that. So the what is gamma ray? So as I said, this is a nucleus can have excited state. So this is an excited state of the nucleus. Now it can come down to lower energy state, which is the final state. Now how it can decay? See, this decay can take place in various ways. It can decay by beta or alpha, it can decay by proton or neutron, it can decay by internal conversion in electron, it can decay by fission or by gamma emission. But in most of the cases, gamma emission is usually the dominant decay mode in the nuclei. So if you can detect these gamma rays, then you can say about the nucleus. And as I said, the nucleus rotates, right? So and all these these collective excitations of the nucleus was formulated by Bohr and Mendelssohn by very very beautiful and very simple picture, and they resembles the classical equations of rotor. And you know this is L is equal to moment of inertia into omega, the angular frequency, and you can get the energies, right? You can write the energies like this way from our higher secondary books. And now if we change this L, this angular momentum, to a angular momentum quantum number I, then you get this equation. Now the question is whether you can get this Ej, this energy corresponding to sorry, this is not J, this I, this angular momentum of the states of the nucleus which obeys this relation. And if you get the excited states of the nucleus like this, and with energies in this kind of units, and if you plot these energies as a function of the angular momentum, then you might get a parabola corresponding to this equation. And if you get it, then you can say that the nucleus is actually rotating and rotating like this. And of course, as I said, this rotation is a collective motion. And then not only they when they gave this theory, and soon after that, this type of states, 0 plus 2 plus 4 plus 6 plus, these states in 176 hafnium nucleus and 180 hafnium nucleus, 0 plus 2 plus 4 plus 6 plus, were identified from the beta decay of lutetium and 176 lutetium 180 tantalum nuclei. And these were, and these see in these are the experimental energies, and these are the energies which they obtained from their equations, parabolic equations, and they match very well. So this is another very pioneering, this is very interesting discovery, that the nuclei, which is a quantum mechanical object, but also follow the rules of the macro world in a little bit quantum mechanical way. And so they also get this Age Bohr, who is the son of Niels Bohr, and Ben Roy Mottelson, and Leo James Rainwater. They got Nobel Prize in 1975 for their connections, for the discovery of the connection between the collective motion, the particle motion in atomic nuclei. So, if you show all this dancing of the nucleus, then you have to see it through the window of gamma ray spectroscopy. Look through the, of course, not like this, but you have to do some experiments. How do you do that? But what is spectroscopy? What is gamma ray spectroscopy? So spectroscopy, you know, it is we have read in the in our BSCs and all those, that it is a dispersion of colors, right? And colors means what? So colors means frequency, and so dispersion of frequency, and frequency means what? Frequency means energy. So dispersion in energy. So this dispersion in energy is the spectroscopy. So dispersion in the energy of the gamma rays is the gamma ray spectroscopy. And you see this in the gamma ray spectroscopy, these are different peaks corresponds to different energies, which is the different colors here, and the height of these peaks corresponding to intensity of this each color, and there is the count in each one. So that's what the gamma ray spectroscopy. We have to get this kind of picture, and then analyze this picture to get the about the nucleus. And to learn many secrets of the nucleus, you have to put the nucleus in extreme conditions of high angular momentum, high temperature, or large ratio of the neutrons and protons. And then again and again, I say that gamma spectroscopy is the tool to see this. Okay, this is the chart of the nucleus, and this is the playground of the nucleus structure physics and the gamma spectroscopies throughout the world. And what it is? This is the neutron numbers is plotted in the x-axis, and the proton numbers are plotted in the y-axis. And all these small boxes are the nucleus, for which there is a certain number of protons and there are certain numbers of neutrons. And all these black dots or the black squares are the nucleus, which are the stable ones, and all the other ones are actually the unstable. And people are trying to produce this nucleus and study all these nucleus, including the stable as well as the unstable ones. Why? Because in all these nuclei there are various interesting aspects. I'm not going to the details of this, but in various regions of this nuclear chart you get various things. So, for roadmap of gamma ray spectroscopy. for study the nuclear structure. It has the, we have to first produce the nucleus at high angular momentum by nuclear reactions. We have to detect the gamma rays then, and then build up a level scheme, and then interpret the level scheme. That's it. So there are only four steps by which we can study the gamma spectroscopy. Let's go one by one. If we for the production mechanism. Now, there in the production mechanism, if it's here, since we are producing the nucleus, so we have to do some nuclear reactions to produce the nuclei, and so there are certain reactions that you can do. And so, for example, this is one nucleus which is called the target nucleus, which is stationary, and there are another projectile nucleus which is hitting this target nucleus, and this can hit in different places, right? It can hit head on or at different places, and which is called the impact parameter. And depending on this impact parameter, different reactions take place. Now, one of the most important reaction is the fusion evaporation reaction, which is used by this nuclear structure physics, gamma spectroscopists, and I will explain them a little bit more for the students. So this is the fusion evaporation reaction. This is a target and this is a projectile. So now this projectile goes and hits the target and creates a compound nucleus. And this compound nucleus, if it is in the excitation energy angular momentum space, if you see, so this is a high excitation energy of like, let's say 70 MeV of excitations around that, and angular momentum of more than 30 H cross or so. So what it will do, it will this compound system will emit the particles. So particle will be evaporated. That's what the name this fusion evaporation reaction. So after evaporating these particles, this excitation energy will come down to about 10 MeV or so, and then it cannot do particle emission, and then it can go to the ground state only by emitting the gamma rays. And this line by which it goes through this to the ground state is called the Erast line, which is the minimum energy line for a given angular momentum states of the nucleus. And the gamma ray in and around this Erast line that we detect from this nucleus, which comes out and we detect in the detector. And around this Erast line, there are several interesting physics which is going on here, and like band termination, collapse of pairing, and magnetic rotation, identical bands. There are various things. So these things these hyper deformation. So this we study. So this is a different nuclei and different places of the Erast line. So that you have to remember. Now, for that, what we need a particle accelerator for the nuclear reaction to happen, and we need a detectors to detect the gamma rays with high resolution, because we have to separate the gamma rays. And in India, we have the different accelerators. So, for example, we have in Mumbai and Delhi, we have the Pelletron accelerators with Linac booster, and at VCC in Kolkata, we have the Cyclotron accelerator. And I'm not going to the details of how they work, but at VCC, which is Variable Energy Cyclotron Center, so this is one of the major accelerator centers in India, and it has 3 cyclotrons which are running. So one is K130 cyclotron. There is the old one, very old one, and we have with us Professor Srivastav, who was the former director of VCC Kolkata, and and also we have the K500 superconducting cyclotron, more powerful, and we have cyclone 30 medical cyclotron, which is for producing medical isotopes like fluorine 18, FDG, etc., for the purpose of the medical therapy and diagnosis. But the experiments now, which I'll show and which we have been doing until now, is with K130 cyclotron, and soon we will do experiments with K500 cyclotron. And there is some uniqueness of these cyclotron machines even within India. And by the way, the cyclotron was invented by Ernst Orlando Lawrence, and who also got Nobel Prize in 1939 for the invention of and the development of cyclotron and for results obtained with it, especially with regard to artificial radioactive elements. So it was built for this purpose only. But this is also have medical usage throughout the world. So now, after we produced, we have to detect the gamma rays. The gamma rays are detected by some detectors which is called the HPG detectors, which is a semiconductor detector. And this HPG detector, HPG is a crystal which has to be cooled in liquid nitrogen temperature. So this is a HPG crystal. There are some anti-compton shields, etc. And this is an actual detector, which is basically a old one, but we have a very new detectors here. So this is a HPG crystal, and this is a liquid nitrogen viewer, because you have to put liquid nitrogen here to keep the detector cool. And then it has a very good resolution also. Now what is done is, then from there, from the detector, you get electronic signal, and you process this electronic signal, and then after that you get some numbers from this processing of the electronic signal, and this digitized output is given to the computer. And what computer sees after we process this data, then we see a picture like this, which is a spectrum of energy versus counts. This is, for example, spectrum of 137 cesium source, which emits beta and then followed by the gamma. So this 661 keV gamma is seen as a peak here in our computer. And nowadays, this is somewhat old picture, and nowadays, actually, this one detector is replaced by several detectors, a multi-detector array, and all these electronic circuits actually replaced by digital data acquisition system, in which you just put these pre-amplifier signals, these detector signals there, and you get the outputs. You do not need in between all these electronics modules and all those things. And you see this in HPG detector, how it is superior to other detectors. For example, sodium iodide detector is scintillator detector. So there are two peaks in cobalt 60 source, 1.17 MeV and 1.33 MeV. So they look very close to each other in sodium iodide detector. But you look at here, when you look at HPG detector, they are very narrow. So if there is some peak, some other gamma ray in between these two, you can see it in HPG detector, but not in sodium iodide detectors. So you better use HPG detector for gamma ray spectroscopy. And in India, we have INGA detector array, the Indian National Gamma Array, which is a collaborative effort. And this is an array of Clover HP detector. This is again an HP detector, but it is some special kind of detector, which is a Clover in a Clover geometry. There are 4 crystals inside one detector, and it's a national facility which moves between the 3 accelerator centers that I showed: this TIFR Mumbai, IUSC New Delhi, and the VCC Kolkata. And it can be possible to couple with other detectors also. Now, at VCC, we have, apart from this INGA, which you can use for different experiments, we also have another facility which is called Venus, which is again the same HPG detector, HPG Clover detector, but it's in a different geometry. So this is in a horizontal geometry. There are certain advantages of it, and that's we call the VCC nuclear spectroscopy array, and with a certain number of detectors. And these are also, we have done several experiments with this Venus as well as this INGA. And Venus, and this has been set up by all our students, along with all our junior members and the senior members and the other engineers, and all of them. They all work together to make this setup a realizations, with several experiments done. And this Venus actually setup appeared in 2018 issue, April issue of Association of Asia Pacific Physical Society Bulletin, with some physics aspect discussed, as well as the setup of measuring photons from rotating nuclei. So this is actually some important machine and important setup. So there are gamma ray spectrometers all over in the world also. There are not many, but quite a few. And for example, there are some bigger arrays, like this is a gamma sphere array at ANL, this Argonne National Lab, with 110 HPG detectors, but these are not Clover detectors. Then there are exogam, and then there is Ganil at Ganil in USA, in France. Then there is Uhaspira at Uhaskila. This is again in Europe. Then there are others in Canada. There is a Tigris in Triumph. So these are a little bit these Clover detectors, but the segmented Clovers. So there are several detectors, several arrays exist, and this is the new age, the next generation detector, which are the tracking detectors. There's one in USA, which is called Greta Gamma Ray Energy Tracking Array, and one in Europe, which is the Agatha Advanced Gamma Tracking Array. And actually, we collaborate in this Agatha detector. In fact, yesterday we completed one experiment with Agatha detector array in Ganil, and we actually, basically, because of this pandemic situation, we could not go there for the experiment, but we participated online. But for the formulation of the experiment, we participated, and probably will also analyze some data of it. And these are very large collaborations from Japan to USA, so there are large collaborations, large international collaborations. We are also part of it. So these are the tracking arrays in which you track the gamma rays where it is going and get the energies. So now we have this. We have produced the nuclei, we have detected the gamma rays, and now we build up a level scheme. What is a level scheme? Level scheme is nothing but the levels of the nuclei, and which are connected by the gamma rays. And so this is a very small level scheme that I saw. And what it has? It has these energies, this excitation energy of the levels, and it has the spin and parity of these levels. And sometimes it also has the lifetime of the state. And what kind of gamma rays are these? This is this, whether it is a M type or E type, or it is one type or two type. It is M1, E2, E3, sometimes something like this. And so this we get from the between the correlation we get the correlation between the gamma rays. That's why I need many detectors to get the correlation. We also the spin parity of the states we determine from the correlation of the angular correlation of the gamma rays, angular distribution of the gamma rays or angular correlation of the gamma rays, and also the polarization of these gamma rays. And also we measure the lifetime of the states. These are some technical things about the making matrix to get the correlation, etc. And this is another level scheme. So we step by step we measure we get the level scheme. And lifetime measurements is actually very important aspect in nucleus gamma ray spectroscopy nuclear structure. And this lifetime of the nucleus state vary in a wide range. And the other day we were listening to one talk, and this varies from like 10 to the power 32 orders of magnitude that we measure lifetimes. So there is not one single method that you can measure this in that wide range, but it has several methods of measuring. But in all these methods, it uses the gamma ray de-excitation law, which is this e to the power minus t by tau. This de-excitation law it follows. This is a power law. And just to give you one example of one technique, which is the pulse beam technique. What is the pulse beam? This pulse beam means this is a projectile and this is a target, and the projectile is not coming continuously, but is coming in bunches, one bunch, then another bunch, and the reaction takes place and gamma ray comes out. So that's what this pulse beam is. And in this pulse beam, so suppose one pulse beam comes, and then we also have a detector here, and we have a stopwatch. This is just for example's sake. And we have a target. So now this pulse beam comes and here's this target. And now as soon as here's the target, we start our this stopwatch. And then we'll stop the stopwatch when this gamma ray comes and hit the detector. So that now my stopwatch stops. And then you record this time. And now this can go on for several gamma rays, for millions of gamma rays. And we record this time for each of the gamma rays and see how many counts for different times. And we replace this stopwatch by electronic circuits, of course, because we don't see the gamma rays. So then you can get a curve like this, where you get the number of counts for each time interval of this, as I said, this 10, but you can stop at various times. So how many 10s we get, how many 9s we get, things like that. So that is the time distribution of this. And if you plot it, and so this follows this law, e to the power minus t by tau. So if you put it in the log scale, so there is a linear. And if you see in the experiment, so if you see in the experiment, this is experimental data, and see exactly this is a linear thing as you expect from this one. And what is this one? The green one. So this one is actually prompt. So it decays very quickly. So there is very small half-life. This has a half-life of about 43 nanoseconds in a nucleus which is 139 PR. And you see it is this one. So this is this state, which is the 708 keV gamma rays, this black one. So this decays very slowly, this 43 nanoseconds. This 900 keV is this one, which decays very fast. This lifetime is not known, but it is less than 1 nanosecond. So this decays very fast. So that's how we can get the time of the each level of the nucleus. Now, what do you do with this level scheme? So, by the way, this is another level scheme of a nucleus. So, this is the levels connected by the gamma rays, and it has the energies and the spin energies and the spin and parities. Now, what do you do with this? How do you relate this with the structure of the nucleus? So, for example, you can get a level scheme like this. It looks very complicated, but to a gamma ray spectroscopist or nuclear structure physicist, if you ask, then he can rightly tell some specific features of this. For example, he can tell you that there is no regular sequence of levels here. So there is a kind of haphazard. So this must be particle excitations and single particle excitations. And if you remember from the beginning slides, that then that is a property of a spherical nucleus. The single particle excitations, kind of excitations, this is going on inside the nucleus. So if you get this, so this 143 summary, we can say this is spherical kind of nucleus. But if you if you show them, the nuclear structure physicist, a level scheme like this, then you can also now see that there is a regular sequence of levels. Now, if you feed these levels with E versus I or E versus angular momentum, then you can see that this will fit a nice parabola, and then you can see that means it is this collective motion of Bohr and Mottelson, and then that means nucleus is rotating and generating this kind of levels. So this is rotational bands, and rotational band is possible only for the deformed nucleus. So that means this is a deformed nucleus. So this level scheme tells me whether it is a spherical nucleus or deformed nucleus, or even more. These are the very simple things, but then there's some more. For example, if you have a level scheme like this, then you can say this kind of Sears band, which is something else, some different things, which I'm not going into the details. So I choose actually these examples because these are all done at VCC with Inga facility at VCC. So there are different nucleus and different kinds of bands and different kinds of level structure and different kinds of physics that you can get from knowing the level schemes or the level structures of the nuclei. Now, in this again, this is the N versus N nuclear chart. If we show, so what we did in this with this Inga at in India, what we do actually, I have been involved in the study of all these nuclei in these different regions of the nuclear chart. And you remember, in the different regions of the nuclear chart, there are the different physics aspects were there. So we have found different physics aspects in this, which is some of them are actually in broadly they are mentioned here for different regions of the nuclei. And these are using heavy ions and alpha beams at TIFR, IUAC, and VCC. So these are our setups and the instruments, and these are the what we did. So now I give you just one example at the end. I'm probably over time, but very quickly on a gold nucleus that we have recently studied, and gold glitters. So of course it glittered ultimately. And what we tried to do, or what we have found, is a oblique motion of a nucleus of this nucleus of this gold nucleus. And what is the oblique motion? So you have I showed you a rotational nucleus, this deformed nucleus which rotates. Now you have seen this rotation is fine. You can very well understand, and I shown you a picture of a top which you can rotate, right? But you must have seen this toy when it rotates. Then at the end of its rotation, when it is just stopping, just before it gets stops, it wobbles. So it does not rotate very well defined manner. It has another motion around another axis. So suppose it rotates around the axis, but it wobbles around another axis. So that kind of motion is called the wobbling motion. So the thing is that if I correlating this our classical motions in the quantum worlds, So I should see all those classical motions also. Or the question is whether I can see whether my model actually predicts and can explain all these motions, and of course whether this is in the theory or we can see in the practical, in the real nucleus itself. So this oblique motion is actually this very interesting motion which has recently been identified only in a few nucleus, in a nucleus which is triaxial in shape. So that means it does not have any axial shape. So this nucleus is like this, in which it has three axes, but all three axes are different in length. One is a long axis, one is medium axis, and there is another which is short axis. And so you have moment of inertia along all these three axes, which are also different. And the nucleus prefers to rotate around its medium axis, because this medium axis has large moment of inertia. And moment of inertia comes in the denominator, h cross over by 2 into moment of inertia. So it will have minimum energy. And everybody, including a nucleus, prefers this the minimum energy. So it rotates around the medium axis. But it also has rotations around the other two axes. And then this when this nucleus also try to rotate the other two axes, so then it gets some coupling between these two, all these motions, and then it generates a precision of this medium axis rotation, and this gives the oblique. And this was actually predicted long ago by this Bohr and Mottelson, as I told. So this is, since they are in their model, it should come, because this is a classical analog. But this was, and this they talk about the symbol wobbler, which is shown in an even nucleus, which is even number of protons and even number of neutrons, but that is not yet experimentally identified. However, this motion has been identified in a few odd A nucleus, in which there is an odd number of protons or odd number of neutrons. And when there is an odd number of protons and odd number of neutrons, then it can couple to the rest of the nucleonic system. So that means rest of the nucleus. This is the odd protons or the odd neutrons. It can couple like this, in which it is moving around in that directions, or it can couple like this, which is moving in these directions, which is its longer axis. Okay. So depending on that, I'm not going to the details, but depending on these two couplings, so you can get two different kinds of these oblique motions. One is called the longitudinal oblique, and another is called the transverse oblique. Now, this is for some experts. When this odd particle is low omega orbital, so this gives the transverse oblique, and the others is the longitudinal oblique. So I'll come to that again. So as I said, so there are two different pictures, the two different coupling, which generates the longitudinal and travels to different kinds of oblique phenomena. And this has been recently, for odd nucleus, modeled by Freundorf and Donau. This is Stefan Freundorf, who is in the USA, and gave the oblique energy, the energy of this oblique motion, by some complicated looking equation, in which this I curly I is the moment of inertia, but this is very simple actually. And this small j is this angular momentum of the particle, and this j, which is equivalent to I, the spin or the angular momentum of the nucleus. And you have for the transverse and the longitudinal, this I1, I2, I3 are, and this IL, IM, IS takes different values. So these are the details. You don't have to go into the details for the basic understanding. But that's how this formulation is done. So you have different, then you have for the transverse and longitudinal, you put different values and you get different kind of things. And in around this is again the nuclear chart. So because we have to show our playground, right, again and again. So where to show where we are. So we have like 270 stable nuclei, we know. So this is the black ones. And but there are 3,000 nuclei that we know to exist right now. But out of all those 3,000 nuclei, only these nuclei show, or this until now, these oblique motions. And this also has this longitudinal as well as the transverse oblique. And the oblique energy actually experimentally seen, for some of them this goes down with the angular momentum or spin, this angular momentum and spin, the spin is not the s, the spin, but it is also the angular momentum. Is the angular momentum. So consider whenever there is a spin, you consider this angular momentum. So this oblique energy decreases for some cases with spin or angular momentum, and for some cases it increases. So so one is the longitudinal oblique, for which it is increasing, and one is the transverse oblique, for which it is decreasing. So that's how this in these ones, in these nuclei, in these nuclear oblique nuclei, they identify whether it is a longitudinal or transverse oblique. And we have identified oblique motion 183 gold nucleus, in which there are Z is this 79 number of protons. But this is the different from the rest of the nuclei, and I'll show how it is. And the difference is it has got two oblique bands. In all the other, there is only one oblique band observed, and it has a different behavior of the E oblique and the energy, the oblique energy, and I'll show how different it is. So the experiment was done at VCC in Kolkata with a 20 neon beam. So there is a heavy ion beam of 20 neon, which you cannot get anywhere in India. So this is you can get only in VCC Kolkata, 20 neon beam. And then our target was 169 thulium. This is another nucleus. This is another element, 169 thulium. And we hit this 169 thulium target by 146 MeV of 20 neon beam, which we get from the 130 K130 cyclotron. And we produce this 183 gold nucleus after it has evaporated 6 neutrons. So I showed you how these neutrons gets evaporated, neutrons or protons, and this residual nucleus is 183 gold. And this 183 gold then emits the gamma rays, and these gamma rays are detected in this Inga spectrometer here with this HPG Clover HPG detectors. And this is our target. This inside this target chamber we have these targets, and this is how this reaction cross section was of this 183 gold. And these are the measurement and the analysis. This is technical details. This is the correlation of the gamma rays. This is the angular correlation of the gamma rays. This is the energy correlation of the gamma rays, and the polarization of the gamma rays. This we measured, and then we come up with something called the level scheme of the gold nucleus. So this is the level scheme of the nucleus. So first thing you see that these are the this is a very regular levels, right? So this is a deformed nucleus. Of course, the deformed nucleus. This is a oblique motion needs deformed nucleus. And this 183 gold we can identify. So this Z is equal to 79, proton number and neutron number 104, but we can think it as a 182 platinum nucleus, which is Z78 and neutron number 104 plus one extra neutron. So and this neutron couples with this core, and this coupling can be different, and this coupling and this one neutron can be in different orbitals. So when it is in the H9 orbital, then you get a band. This is rotational band. This is or when this neutron is in the H9 orbital. You know this. I showed you this orbital. This is of the neutrons and protons. So it is this orbital, and then the nucleus is rotating. And also there is another I13 orbital. So when this neutron is an I13 orbital, then it's rotating, then you generate this rotational motion, this band. So there are these two bands, and we have beautiful gamma ray spectrum. With this gamma ray spectrum, analyzing several of the gamma rays, we have analyzed this and come up with this. And we have identified this band. This is TW1 band, we say, this transverse oblique band, and this band. So these two bands we have identified after going through various rigorous analysis techniques, and this is the oblique bands of this in this nucleus. And one of these analysis is the DCO. We call this DCO, the directional correlation of oriented nucleus. This angular correlation we are talking about, and we have plotted it. And then these are the experimental values, and these are the theoretical values. We can calculate and then find out some values of this, and basically we identify the something called the delta, which is the mixing ratio, and from which is a crucial evidence for the oblique nature. This I give it as one example how we have told that there is an oblique motion in the nucleus. There are some other things also from which. And then we have also find the experimental oblique energies, and we saw that there are two bands, right? One is the negative parity H9 half, and there's positive parity I13 half bands. So in these two bands, we see there's oblique energy in one decreasing and in one case it is increasing. So we could very well we could go by the wave what the people are doing, and then we could say that okay, negative parity is transverse and positive parity longitudinal, and the story is over. But actually, we find there is a very nagging problem. I mean, we are not getting satisfied. Why? Because there are some conditions, as I told you, these conditions of the how this gets coupled. And so this all this when this odd particle, this longitudinal oblique happens when this odd particle lies in the middle of a GSL. I am telling, I am just what is the middle of a GSL, what I mean by that. And this odd particle which is the bottom of the GSL, then it gives the transverse oblique. So there's two different couplings. But this is the same nucleus, this 183 gold, and this we have this H9 half configurations, means the particle either is H9 half or an I13 half. What are these orbitals? So these are the again the level structures of the nucleus, and these are the H9 half orbitals. This is a function of deformation how it behaves, but this is the H9 half orbitals, and this is the I13 half orbitals. But you see, these are all H9F orbitals, and this orbital lies at the bottom. So all these 1, 2, 3, 4, 5, all these 5 dotted orbitals are actually H9F orbitals. So, but this Z is equal to 79. So 79th proton, this is 82, 82nd proton. So this is 78th proton will be here. So the 79th proton will go any of these orbitals. So that means it has gone to this orbital, not to these and these orbitals. But since it has gone to these orbitals, and these orbitals are actually lies in the bottom of this H9 half cell. Similarly, all these levels which are continuous lines are the belongs to I13 half. So if it goes to I13 half level, so it also lies at the bottom of this I13 half levels, not to the up. So in both the cases, it is the bottom of the GSL. So that means it is never going to the middle of the GSL. So it should show the transverse oblique. So the picture is not matching. So not matching for the oblique excitations. So these are both the should be transverse oblique. But the thing is that how do I then match how do I think their behavior of this experimentally that you obtain the behavior of the oblique energy as a function of the angular momentum of the spin or the eye. And then we went through that Freundorf's model, Dunlop-Freundorf's model, and then we generalized it. So it is generalized it from a very low angular momentum to very high angular momentum. And then we have seen that in both the cases, it matches with our calculations. And and then we have extended this our calculations, the generalized model, to the other nucleus for which this transverse oblique has been already observed. This 135 promethium and 105 palladium nuclei. And you see, for these nuclei, these were the experimental points are decreasing. Experimental points are decreasing. But in our model, which we have calculated, these are the blue curves in all the cases, which has a increasing part and then decreases. So all the nucleus are increasing part, but all of them until now were showing only on this decreasing part for the transverse. So we did not know that there is a theory also predicts an increasing part in the beginning, because it was no nucleus actually showed this increasing part. So this was not known earlier. So nobody calculated that. So we have seen the experimentally these points which are falling on this increasing part of this oblique frequency or oblique energy, as well as we have modified this theory to include this part, and which matches now, which is now more general model and matches all the nucleus, not only in our in the 183 gold which we have studied in both the band, but for the other nuclei. And you see there is a maxima here. For all this, theoretically there is a maximum, and then it in which on both of this there is this maximum corresponds to IM. This we call this IM on both sides of the IM. The E oblique falls, it decreases. So this we have This we have put it in a paper and then published. And this depends on whether, and you see this for this case, why you have observed it, because the IM is actually very large. So for this we have this 16.5 H cos, which is large. For other cases, the IM is actually lower than the values, experimental value is. So that means everybody is in this part. So this we have discussed in our paper also. So this is the, and now this is, and this has got published in physical review dated journals. And I am telling you that all these things we have done, and you might have the impression that I have done all these things, but no, this is this my PhD student Somen Nondi, who has done all these works, all this analysis, this painstaking analysis and all those things. And all these collaborators actually involved in every part, like in the experiments and then the data analysis part, and all these things, they are involved. And so that actually brings to the end of this. And so if we summarize what we have told until now, that gamma ray spectroscopy is a powerful technique to study the structure of a nucleus. The level scheme of a nucleus deduced from the gamma ray spectroscopy is the fingerprint of nucleus shapes, as I mentioned, for deformed and spherical and all others, and cell structures. And on the oblique motion that we also have found out is from the level scheme of the nucleus. And various nuclear reactions like fusion, evaporations, and all the reactions used, but fusion evaporation is the most dominant for this nuclear structure used for the nuclear structure studies, and which produce the nucleus at high angular momentum. And the gamma rays, which de-excites along or close to the Eras lines, are detected by using these germanium detectors, which has a very good energy resolution. Many experiments have been performed using the Clover HPG detector array at Inga and Venus array, and many more to come in the in future and near future and next future also, late future also. And we have, I show you one example, only one example, the general features of transverse oblique motion in 153 gold nucleus, and which has been, we have discovered a general transverse oblique motion of the nucleus. And these are all my, all the collaborators we have contributed in this, and this has a, these are people from all the three institutes from Kolkata, from VECC, from Science Institute of Nuclear Physics, which is next door, and also the UGC DACSR in Kolkata. And I would like to say my homage, actually, I pay my homage to Professor Asimananda Goswami, who is actually pioneering in setting up this Inga setup at VECC. And but unfortunately, who is no more with us, but his works and his setup remains, on which we are doing all these experiments. Thank you.
So thank you, sir, for your wonderful presentation. So
Sorry, probably
thank
I
you.
over time, but yeah, if you have some
It's
questions,
okay,
I
sir.
can.
We have got few questions. So if you allow,
Sure.
we can start. We have a guest with us, Sir Dinesh Srivastava, sir. I have connected him. So, sir, good evening and thanks for joining with us. Hello, sir. So we have
Good evening, good
few
evening.
questions. Okay. The
Yes, sir.
first question: why do the nucleus after iron 56 can't take part successful fusion reaction?
Why? Sorry, why? Nucleus are
Why the
not.
heavy nucleus like iron 56 can't take part successful fusion reaction?
Yeah. Okay.
I think he has in mind the fact that
Yeah.
binding energy per electron for iron 56 is
Yeah.
highest.
Yeah. So this is so let me show you this. Yeah, I got the question. So the you see, this is this nuclear chart. Okay. So now you see this iron is somewhere here. This is 28, so this is so somewhere here. So this is iron. So in which you see this is from here to iron. This part of this and I showed this is the these black ones are the stable nuclei. So all the nuclei we up to stable iron it actually follows almost n is equal to z line, almost like n is equal to z line. Okay, see these lines goes through this n is equal to z. I think there is some problem, but this line also goes through it, goes through here also, or close to that. So this is n is good, but as you go higher and higher, then these curves actually bends towards the neutron number. So you need more neutrons, and and that is because you need more neutrons to overcome the Coulomb barrier, and so with this fusion, and because but if you do the fusion of these two nucleon below iron, then you end up where here, which is in the near the n is equal to z line, but n is equal to z line is going away and away from the stable line. So you cannot get any stable nucleus. You cannot get any stable nucleus by fusing the nucleus below iron, but you have to do something else to get this stable nucleus, because you need more number of neutrons to get this stable nucleus, to get this stability. And you can see, you
Okay,
can
sir. Thank
describe
you.
this
So
with
we have
our your binding energy curve also.
yeah. So thank you, sir. We have another question. So why detector is so which detector is better for gamma ray spectroscopy?
Ah. So as I told already, that the HPG, which is hyper pure germanium detector, is so far the best detector for the gamma ray spectroscopy, because it has the best resolution. So, but some, and there are some scintillator detectors like sodium iodide, barium fluoride, which is also used in gamma spectroscopy, but this doesn't have that much of good energy resolution. It cannot separate. As I showed in an example, that in sodium iodide detector, so the peaks are very broad compared to the ones you get in a germanium detector or HPG detector. But if you need to get the time of the states of the nucleus or nuclear levels, then you should use these scintillator detectors like sodium iodide, barium fluoride, and because these scintillator detectors have very good timing resolutions. Any scintillator detector has very good timing resolution compared to the germanium detectors. And recently, there are some new scintillation crystal, and there are some scintillators have been invented or some discovered, like lanthanum bromide or cerium bromide, which has very good timing resolutions and also much better energy resolution than sodium iodide and barium fluoride, but not as good as HPG. So people are also using lanthanum bromide and cerium bromide for timing and some spectroscopy also. So that's how. So depending on what you are doing, you have to choose. But for if you do want to do the spectroscopy, energy measuring energy, then HPG is the best.
Okay, sir. Thank you. We have another question. So what is the oblique energy?
What is the oblique energy? Yeah. Okay. Actually, this is the energy of the oblique states. So you have the one going wrong direction. You have the another band structures which is coming by the side of your normal rotational band, which we call the oblique band. Now if I say that this energy of that band with respect to this normal this rotational band. So you should this is this oblique band TW1, which I call. So these are also the states with the same spin and parity. Let's say 27 half, and there also sorry, this is 27 half, this 29 half, this 33. So these two becomes the H9 half band, this normal regular rotational band. So this has both 19 half, 21 half, 23 half, 25 half, 27 half, 29 half, etc. Now this also has this 19 half, 23 half, 27 half. This stays this oblique. This is the oblique band. And in these, so the energy difference between this rotational band and the oblique band for the same spin state is actually the oblique energy. So this we can also get from the energy spectrum, which is called the experimental oblique energy, and that's how it is. These experimental points are obtained from this energy difference between the different oblique bands.
Okay, sir. Thank you.
So
So we have
difference between
another
the
question.
main rotational band and the oblique band.
Okay, sir. So what is the gamma ray spectroscopy of positron annihilation, and what facts it can reveal about our universe?
Now, what signal? What is the second part?
Okay, I can add the question. So can you see the question?
Let me see.
Just read below.
What is gamma ray spectroscopy of positron annihilation, and what facts it can reveal about our universe? Okay, so I think for the positron annihilation part, Dr. Pretam can tell better. But
Yes.
the thing is that what is annihilation? What is this positron annihilation? So when the what is positron? Positron is the antiparticle of electron, right? So now when this positron and electron come together, and when it is like not a very high energy, and not a high velocity, so then not doesn't have large kinetic energy, then it annihilates, and annihilates means then it vanishes and gives two gamma rays. And what is the energy of the gamma rays? The energy of the gamma rays are 511 keV each. So for the moment conservations of momentum, you have to get two gamma rays, and each will have to have 511 keV, which is the mass of each of the positron and the electron. Now this positron has very and there's many applications, even in this your PET and all these things, that medical imaging, that also uses this positron annihilations. So this, but since they are the gamma rays, this 511 keV gamma rays, so these are these gamma ray spectroscopy techniques are used to detect these gamma rays for any applications for that. So that's how this gamma ray spectroscopy is involved in this positron annihilation spectroscopy. So you use these germanium detectors also if you want to do the energy, or since the energies you already know for 511, and you want to do the better timing and the position resolution, so you use sodium iodide or scintillator detectors, which has higher efficiency and higher timing, and also smaller detectors you use, so that you get the good position sensitivity. So these are the things that you need for the applications of this positron annihilation spectroscopy.
Sir, thank you. Sir, this may be the last question. So, uh, so did you got any experiment evidence of prions which are
Is that the questions?
conceived
Did we
the,
get any experiment?
yeah, subcomponent of the quarks and
So the
lepton?
question is, did we got any experimental evidence of prions which are conceived to be the subcomponents of quarks and leptons?
Quarks and lepton.
Well, I have no idea, but if Professor Srivastav can throw some light.
The answer is no, not yet.
Yeah, not yet. Okay, sir.
Yes. Okay. So
Yeah.
yeah. So this is
So thank
beyond
you.
nuclear physics, and probably beyond this present particle experimental particle physics.
So thank you, sir, for your wonderful presentation and exciting discussion session. And thanks, Dinesh Srivastava, sir, for joining with us. It was a great webinar, sir. And the main aim of our program is to motivate our students. And as you have explained from very basic to experimental research level. So I think it will definitely motivate our student, and some of our students may fall in love in nuclear physics and gamma ray spectroscopy, and will join later in this field. So thanks again for giving us this opportunity to arrange such an important webinar. So bye for today, sir.
Thank you very much for arranging that. And if you have any
Yeah, it's
further
my
questions,
pleasure.
I've given my
Yeah,
email
of course,
address.
sir.
You can, of course,
Yeah, as the
contact
video
and
will
connect
still
to
remain
me
in
or any
YouTube
of us.
and Facebook, and so if I
Yeah,
got a question, so I'll send to you, and I'll
sure.
send them your
Sure.
email ID also.
And thank you very much for
So
arranging
bye, sir.
this. And really, it is
My
very
pleasure,
good.
sir.
And thanks to the Department of Physics of Pabna University of Science and Technology. That's a very good. I would say this is a very good opportunity for the
Yeah,
students also
it's my
that they
pleasure,
have
sir. It's our pleasure, sir.
opened up.
So thanks, sir, and thanks Dinesh sir also for joining with us. Bye.